I don't have a picture of this problem, so I'm going to go ahead and sketch out what I think is going on. So I've got this floor right here, and I've got a box. And the box is sliding across the floor, and it's sliding with a speed of 5 meters per second. As it goes across the box, it tells me there's a coefficient of friction, so I'm going to have some kind of frictional force. Since the box is moving left to right, friction is going to go the opposite direction. Now I'm going to use a cursive F to represent friction. And friction always opposes motion, and it's parallel to the surface, so that's why I've drawn it like this. I don't have any force going to the right because it doesn't say I have any forces going to the right. The box is just sliding as it goes to the right, and it's got friction acting onto it. And what I want to know is, what is the acceleration of the box? So immediately I think kinematics, but when I start to look at this, I really don't have anything. I have 5 meters per second, I have some other force, and I'm looking for the acceleration. So it really doesn't help me. So what I'm going to do to solve this is I'm going to start with the free body diagram, show all the forces that I know acting on the box, and then I'm going to sum up the forces in the x and y directions and solve for A. So let's start with the free body diagram. So the dot represents the box. I want all the forces that act on the box. One of the forces that acts on the box is going to be the force of gravity. And gravity is going to pull straight down. So that's going to be the force of gravity. That's going to be the weight of the box. What I'm going to do is I'm actually going to use mg whenever I talk about the weight, the force due to the weight. Next, if I look at the box is sitting on a surface. Since it's sitting on the surface, there's going to be a force keeping the box from sinking down into the surface. And that force is called the normal force. And the normal force is normal to the surface. Normal means perpendicular, so this is perpendicular to what the surface would be. So the surface would be kind of along this dotted line that I'm sketching out right here. So that's 90 degrees to it. The other force I have is it talks about a coefficient of friction, so I'm going to have friction opposing the motion of the box. So I'll draw friction in that direction, and I'm going to use a cursive F to represent friction. Now, because that's the only force going on in this case, I know I'm going to have an unbalanced force, which is friction. And that unbalanced force is going to cause a net force. The net force is due solely to friction. So this is the net force, and I'm just going to write that down as MA. Now, when I'm doing the net force on my free body diagram, my net force does not touch the free body diagram. And it doesn't touch the free body diagram because it's not a force that acts on the body. It's a result of all the other forces, so it's just kind of hanging out there in space. Okay, let's sum up the forces. So I'm going to sum up the forces in the x direction. And it's either changing speed in the x direction or it's not changing speed. So that means that my choices are to make this either MA or 0. Well, in this particular problem, it's not changing speed. I'm sorry, it is changing speed because there's an acceleration. So because of that, I'm going to use MA. So I'm going to rewrite that actually as MA right along this line. So there's an acceleration going on, and MA reassigns the positive direction. So in this case, going to the left is going to be the positive direction. So MA is positive direction, and friction also goes the same direction. So it's also positive. Since MA and friction go the same direction, same signs. So now that means that MA is equal to friction. Now let's sum up the forces in the y direction. In the y direction, I'm not changing speed up or down because the box is just sitting along the surface. So that's going to be equal to, that's kind of annoying, that's going to be equal to 0. So now I'm just going to say all the forces up minus all the forces down equals 0. So in other words, the normal force eta is equal to mg. Now that's not always true. That's how the forces dictated what is playing out in this problem. So let's see. In this problem, I need MA. I'm looking for A. I don't know friction, and I really don't have a number for the normal force, so to speak. So what I'm going to do is this. I'm going to substitute for friction the definition of friction. The definition of friction says F is equal to mu times eta. Now there are lots of ways to solve it. From here, everything is just math. So there's lots of ways to get to this final answer. I'm just going to show you one of the ways. So what I'm going to do next is I'm going to take wherever I see friction, and I'm going to replace it with mu times eta. So in other words, for my equation at the top, MA is equal to mu times eta. Well, that didn't help me out a whole lot, but I know this. I know that wherever I see an eta, I'm going to replace that with an mg because eta equals mg according to the equation. Now, eta isn't always equal to mg. It's the way that this equation worked out when I set it all up originally. So in this case, ma is equal to mu mg. Hey, that's really nice. That means the masses divide out, which means the acceleration is equal to mu times g. And that's what I'm looking for, is the acceleration. So the acceleration is equal to 0.600, that's mu, time, times g, which is 9.8 meters per second squared. That means that the acceleration is equal to 5.88 meters per second squared. The second part of the question asks, what's the direction of the acceleration? Well, you can see from where I have the net force up there, it points to the left. So that means that the acceleration is also pointing to the left. And that makes sense because, really, this whole thing slows down as the box is moving. So even though it starts off moving from the left to the right, it's slowing down from right to left.